In a moment that will be etched in the history of science, a cosmic event was just reported that has scientists scrambling for answers. On October 3rd, 2025, a discovery by the 3I/ATLAS project unveiled an unprecedented anomaly that defies all known natural forces, specifically gravity itself. Observations made by telescopes around the world, including the Event Horizon Telescope and the Hubble Space Telescope, have revealed a phenomenon in space that cannot be explained by our current understanding of the laws of physics. The strange occurrence was first detected when scientists at 3I/ATLAS, an ambitious international research initiative focused on understanding the most elusive aspects of gravitational waves, encountered an unexpected anomaly in their data. It was as if the force of gravity itself was being manipulated or bypassed by something unrecognized in nature. The source of the anomaly is still under investigation, but early data suggests it may be tied to an unprecedented interaction in a distant galaxy approximately 1.2 billion light-years from Earth. This discovery has shocked the scientific community, throwing decades of theoretical physics into disarray. How could something exist that challenges the very fabric of space-time? What does this mean for our understanding of the universe, where gravity has been the uncontested ruler for centuries? For the first time in history, an object or event has been identified that displays behavior utterly incompatible with the gravitational force as we know it. The research team initially suspected a malfunction in their equipment, but after recalibrating and validating their findings, it became clear this force is real, and it's beyond anything we could have predicted. And so far, no known explanation exists that can account for what's happening. We are left to ask, could this be a breakthrough in our quest for understanding the universe? Or is it the beginning of something even more bewildering? Is this the first glimpse of a force we've never imagined? Or is it a clue that there are unseen layers to reality we have yet to unravel? Scientists are now engaged in an urgent race against time to decode the mystery of this force. With no natural law able to explain its existence, all of physics as we know it may soon need a complete overhaul. Stay tuned as we dive deeper into this breakthrough, exploring the mystery of the 3I/ATLAS defiance, a phenomenon that could rewrite the very principles of the universe. The world of science has always been one of controlled curiosity, where hypotheses are tested, results are debated, and answers, while elusive, tend to follow predictable patterns. But with the recent discovery made by the 3I/ATLAS team, the usual rules no longer seem to apply. This breakthrough has created ripples that have reached far beyond the confines of research laboratories and academia, signalling the potential dawn of a new era in scientific thought. It all began with a seemingly routine observation, a slight anomaly in the data collected from the advanced gravitational wave detectors positioned around the globe. These instruments, designed to pick up minute ripples in space-time caused by massive cosmic events, have been critical in our understanding of the universe. From black holes merging to neutron stars colliding, gravitational waves offer us a glimpse into the most violent and remote corners of the cosmos. But when the researchers at 3I/ATLAS first reviewed the data, something entirely unexpected appeared. At first glance, the data pointed to an irregularity in a distant galaxy over 1 billion light-years away. But upon closer inspection, it became clear that this wasn't just another cosmic event. The anomaly suggested something far more profound. It appeared as though the gravitational pull from a massive object was not behaving according to Einstein's theories of relativity. In fact, the data suggested that gravity itself was being manipulated in ways previously thought impossible. Normally, when a massive object like a star or black hole generates gravitational waves, they propagate through space-time, stretching and compressing the fabric of the universe. This is what we've seen countless times before. However, the new anomaly detected by 3I/ATLAS displayed behavior that seemed to disregard the traditional expectations of these waves. Rather than following the expected pattern of gravitational pull, the anomaly showed signs of what can only be described as gravity-defying behavior. The waves seemed to reject the very forces that would normally dictate their path. This unprecedented finding left the scientific community in a state of stunned silence. What could possibly be happening? Could this discovery point to something entirely new in our understanding of gravity, or was it a data error that, upon further analysis, would prove to be nothing more than a fluke. The team, unwilling to leave any stone unturned, initiated a rigorous reanalysis of their data, comparing it with previous findings and running it through multiple validation processes. It became apparent that this wasn't just an isolated incident. The gravitational waves were behaving differently from anything observed before. Even stranger, the anomaly appeared to originate from a highly stable region of space, a place where no known disruptions, such as colliding black holes or exploding stars, should have occurred. What they were seeing wasn't just a fluctuation. It was as if an entirely new force was at play, one that was actively interfering with the natural flow of gravitational waves. But the deeper the team delved, the more elusive the force became. It was there, evident in the data, but completely invisible to the naked eye. The more they investigated, the more it became clear. This was something beyond anything they had ever imagined. Could this discovery, which they have now named the defiance of gravity, be a natural phenomenon yet to be fully understood? Or is it something unnatural, a cosmic event or anomaly unlike any other in our known universe? For now, the only thing scientists are certain of is that the rules we once relied upon to explain the universe's most fundamental forces may no longer hold true. What lies ahead could revolutionize our understanding of the cosmos. The implications are both staggering and deeply fascinating. If this anomaly continues to reveal itself, and further studies confirm its reality, we could be looking at a shift in how we perceive space, time, and everything in between. The discovery made by the 3I/ATLAS team challenges the foundation of everything we thought we knew about gravity. For centuries, Sir Isaac Newton's laws and Albert Einstein's theory of general relativity have been the cornerstones of our understanding of the universe. Gravity, the force that governs the motion of planets, stars, and galaxies, was long considered an unbreakable law. Yet now, scientists are faced with evidence suggesting that there might be a loophole in these laws, an unknown factor that bends or even bypasses the force of gravity itself. How can a force so fundamental, so central to the structure of the universe, be defied so easily? And if such a force exists, why has it remained undetected for so long? The answers are unclear, but the implications could be profound. The 3I/ATLAS defiance raises serious questions about the very nature of gravitational forces. As Einstein postulated, gravity is a result of the curvature of space-time caused by the mass of objects. Massive bodies like planets or stars cause a distortion in the fabric of space-time, and this distortion is what we perceive as gravity. When a smaller object moves through this curved space, it is pulled toward the larger one. However, what if this curvature doesn't act the way we think it does? The data from 3I/ATLAS suggests that, in some cases, massive objects might not distort space-time as much as we believe, or perhaps their gravitational influence is being altered by something we don't yet understand. This concept isn't entirely new. Over the years, physicists have proposed various theories about potential modifications to Newtonian gravity. Some ideas suggest the existence of invisible dimensions, dark matter, or unknown fields that might influence gravitational interactions. While intriguing, these ideas have never been substantiated by hard evidence, until now. The anomaly detected by 3I/ATLAS seems to defy any of the known explanations for gravitational behaviour. The scientists initially theorized that the object in question, a massive galactic entity, might be interacting with a dense cloud of dark matter or a region of space-time that exhibits unusual properties. However, the data does not support this hypothesis. The gravitational waves behave in a way that indicates something more fundamental is at play. Could the anomaly be a new type of gravitational force, entirely separate from what we currently understand? Or perhaps it's a force that manipulates space-time in ways we can't yet explain, pushing the boundaries of known physics. Theories about alternate dimensions or parallel universes have long existed in the realm of science fiction. But what if the anomaly detected by 3I/ATLAS hints at something more tangible? Could we be dealing with a gravitational loophole, a break in the continuity of space-time itself? This idea doesn't just challenge our understanding of gravity, it opens entirely new avenues for exploration. If gravity is not as consistent as we thought, what other forces in the universe might be similarly unstable or variable? What other cosmic rules could be bent or broken, waiting to be discovered? As the 3I/ATLAS team continues to study the data, the question of whether gravity can be manipulated or bypassed is no longer theoretical. It is now something that must be taken seriously. The implications for space exploration, the nature of the cosmos, and even our daily lives could be nothing short of revolutionary. Could this be the first step toward a new theory of gravity, one that goes beyond Einstein's general relativity? Or is it merely an anomaly, a glitch in the data that will eventually be explained away by future research? As the team continues to analyse the findings, one thing is certain: gravity is no longer the unquestioned absolute force we once believed it to be. This discovery has opened a door to new possibilities, and while the answers remain elusive, the search for understanding has never been more urgent. As the 3I/ATLAS team continues to analyse the data from their groundbreaking discovery, the question of what this mysterious force could be looms larger than ever. If this anomaly truly represents a defiance of gravity, we may be witnessing the emergence of a new fundamental force in the universe. But what could this force be, and how does it interact with the physical laws we have long relied upon? The data captured from the anomaly hints at a force that operates in ways gravitational forces cannot explain. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. The larger the mass, the more these waves stretch and compress the fabric of space-time. Yet this new anomaly doesn't fit the mold of these classic gravitational signatures. Instead of curving or stretching space-time, the force appears to actively cancel or counteract gravitational pull, leading to what has been termed gravity defiance. As with any groundbreaking discovery, a multitude of potential explanations are being considered. One speculative idea is that the anomaly might be a form of anti-gravity, a concept long associated with science fiction. Anti-gravity in theory would directly counteract gravity's pull, allowing objects to levitate or float free from gravitational attraction. But could this anomaly truly represent anti-gravity, manifesting in a way that challenges our understanding of mass and weight? Scientists have been intrigued by the possibility of anti-gravity for years. Some theorists suggest that dark matter or exotic particles might be key to understanding how such a phenomenon could occur. However, until now, no concrete evidence of anti-gravity has ever been observed. Could this discovery by 3I/ATLAS finally provide that proof? Another possibility that has been raised is that the anomaly detected by 3I/ATLAS is connected to dark energy, the mysterious force that is believed to drive the accelerated expansion of the universe. Dark energy, which comprises roughly 68% of the universe, remains one of the greatest unsolved mysteries in cosmology. Unlike gravity, which pulls matter together, dark energy appears to exert a repulsive force, pushing galaxies away from one another. Could the anomaly be an interaction between gravitational forces and dark energy, where dark energy influences space-time in a way that resists the pull of gravity? The idea that gravity could interact with dark energy is not far-fetched. Recent theoretical models have suggested that these forces might be more interconnected than we once believed, leading to phenomena previously unimaginable. Gravity, dark matter, dark energy, and other exotic forces might be part of a much more complex framework than we have understood up until now. This interconnectedness could provide the key to understanding the force detected by 3I/ATLAS. Other, less conventional theories are also being explored. One such hypothesis involves extra dimensions. For years, physicists have speculated that the universe might contain additional dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could harbour forces that we cannot directly perceive in our everyday experiences. If these dimensions are real, the force detected by 3I/ATLAS might be the result of interactions from a higher dimensional space. The anomaly could represent a force leaking from these extra dimensions, influencing our universe in ways that produce gravitational effects we cannot easily explain. Finally, some researchers are exploring the possibility that the anomaly is tied to quantum gravity, a theoretical field that aims to unify quantum mechanics with general relativity. Quantum gravity seeks to explain gravity on the smallest scales of the universe, where the effects of quantum mechanics dominate. What if this anomaly is a quantum event, one that occurs when quantum gravitational effects become detectable on cosmological scales? If this is the case, the discovery would represent the first tangible evidence of a quantum gravitational phenomenon, offering a breakthrough that could unlock new realms of understanding about the fundamental nature of the universe. The true nature of this force remains elusive, but it's clear that the 3I/ATLAS discovery is just the beginning. Whether it's anti-gravity, dark energy, extra dimensions, or quantum gravity, the force behind this anomaly could fundamentally reshape modern physics. Each theory offers fascinating possibilities, but none of them fully account for all the data gathered so far. What remains certain is that this discovery is far from an isolated incident. If this force can be observed once, it is likely that it can be observed again, perhaps in even more dramatic ways. The continued study of this phenomenon promises to open a new frontier of physics, one that could ultimately lead to a more complete understanding of the universe. What began as a simple anomaly in the data could, in time, lead to a revolution in how we view the fundamental forces that govern the cosmos. The 3I/ATLAS project, originally conceived as a high-level experiment to study gravitational waves, has now found itself at the forefront of a new scientific frontier, one that stretches well beyond its initial goals. What began as an ambitious yet controlled experiment to observe cosmic phenomena has inadvertently unraveled a mystery that could reshape modern physics. While the full implications of the gravity-defying anomaly remain unclear, one thing is certain: this discovery is not an isolated event or confined to a single region of space. The first hint that the anomaly might be more than just a statistical fluke emerged when multiple detectors, spread across various locations on Earth, began recording similar disturbances. This wasn't a localized glitch or instrumentation error. Something consistent was happening, something that defied our understanding of space-time and the forces that govern it. The 3I/ATLAS team has been forced to reassess their original assumptions. What initially appeared to be a rare, isolated event has turned out to be part of a larger, ongoing pattern. Researchers now suspect that this phenomenon could be occurring on a cosmic scale, with multiple instances scattered throughout distant regions of space. If this theory holds true, the anomaly could represent a previously unnoticed feature of the universe, a fundamental force or interaction that has remained hidden until now. Given the vastness of the universe, the scope of this discovery is difficult to fully comprehend. The anomaly's reach could span millions, if not billions, of light years. With new data in hand, scientists are now considering whether this force operates universally, or if it is localized to certain regions of space, such as black holes, galaxies, or clusters of stars, where gravitational behaviors are particularly strange. What makes this discovery even more intriguing is that these gravitational anomalies are not confined to specific cosmic events, such as black hole collisions or supernova explosions, which typically generate detectable gravitational waves. Instead, the anomaly appears in regions where traditional models predict stability. It's as though these forces are operating in parallel with our current understanding of space-time, existing beneath the surface of what we know to be true about the universe. The team has since expanded their research beyond gravitational wave detectors. They've begun collaborating with astrophysicists specializing in cosmology, quantum mechanics, and dark matter to develop new theoretical models that might explain these gravitational irregularities. New technology, including space-based sensors and advanced telescopes, is being deployed to search for further signs of this force in distant galaxies and other unexplored regions of space. If these anomalies are indeed widespread, as the data suggests, the team believes this could be the key to unlocking hidden mysteries of the cosmos. The scope of this experiment has far outgrown its academic origins. It is now potentially world-changing. For decades, physicists have struggled to reconcile the forces of gravity and quantum mechanics. These two fundamental aspects of physics have stubbornly resisted integration. If the 3I/ATLAS anomaly is connected to quantum gravitational phenomena, it could provide the missing link between these two fields, potentially leading to a unified theory of the universe's fundamental forces, a theory that has eluded scientists for over a century. The global collaboration that has emerged from this discovery is unprecedented in scientific research. Physicists, astronomers, and engineers from around the world are now working together in ways never before seen. What started as a small-scale research initiative has transformed into a global effort, uniting some of the brightest minds in physics. This international cooperation may prove crucial in uncovering the true nature of this anomaly and determining whether it marks the dawn of a new chapter in scientific exploration. As the team continues to gather data, one of the most pressing questions is whether this anomaly might be linked to other known cosmic phenomena. Could this gravitational defiance be related to the unexplained movements of galaxies or the accelerated expansion of the universe? Could it be influencing the behavior of dark matter or dark energy? While these ideas remain speculative, they highlight the vast potential of this research. The wider scientific community, though cautious, is beginning to take notice. Physicists from various disciplines are reconsidering the foundational principles of their fields. What if the fundamental forces we have always accepted as constants are not as immutable as we once thought? The discovery of this force suggests that the universe may be far more malleable and mysterious than previously imagined. Moreover, this anomaly challenges the status quo of cosmology and astrophysics. Could it lead to new technologies, such as methods for harnessing or manipulating this newly discovered force? While we are far from that point, it's easy to imagine how such a force, if it can be harnessed, could revolutionize energy production, space travel, and even our fundamental understanding of reality itself. The scope of the three I/ATLAS project's findings is only beginning to unfold. While the current data provides tantalizing clues, the true nature of this force and its potential implications will take years, if not decades, to fully understand. The experiment is far from over, and the answers it yields could alter the course of human history. For over a century, Albert Einstein's theory of general relativity has been the gold standard in our understanding of gravity. From the bending of light around massive objects to the behavior of black holes, Einstein's equations have guided our view of the universe. His theory posits that gravity results from massive objects bending space-time, offering an elegant description of how the cosmos works. But now, the 3I/ATLAS anomaly challenges this very framework, posing an existential question. Could there be more to gravity than Einstein ever imagined? For decades, general relativity stood unchallenged, especially in explaining large-scale cosmic phenomena. Yet, when the first data from 3I/ATLAS arrived, it hinted at something that defied relativity. The gravitational waves detected from the anomaly didn't behave as expected, leaving scientists to wonder if this was a data flaw or something far more profound. As the investigation progressed, it became clear that this wasn't just a simple outlier or experimental error. It was something that could reshape the foundation of physics itself. To understand the magnitude of this challenge, we must examine the core tenets of general relativity. According to Einstein, massive objects such as stars and planets cause space-time to warp. This curvature is what we perceive as gravity. The more massive the object, the greater the warping and gravitational pull. For over 100 years, this concept has explained everything from the orbits of planets to the expansion of the universe. However, the data from 3I/ATLAS revealed something unexpected. The anomaly detected seemed to suggest that gravity, in its traditional sense, didn't apply. The gravitational waves didn't follow the expected curve, nor did they stretch or compress space-time in the way Einstein's theory suggests. Instead, they behaved in a way that was impossible under the rules of general relativity. These gravitational disturbances appeared to bypass the expected physical properties of mass and space-time, indicating the involvement of an unknown factor, one that could upend our understanding of the universe. What does this mean for Einstein's theory? Could it be that general relativity, while successful in many areas, is only part of a much larger story? Many physicists have long speculated that general relativity might not be the complete theory of gravity. Some theorize that a more fundamental description of gravity exists, one that accounts for the quantum nature of the universe at the smaller scales known as quantum gravity. Einstein himself struggled with the inability to reconcile gravity with quantum mechanics, the theory governing the behavior of particles on the smallest scales. While general relativity works flawlessly on large scales, explaining planetary motion and galaxy formation, it fails to explain what happens inside the smallest building blocks of the universe. Quantum mechanics, on the other hand, excels in the realm of the very small, governing the behavior of subatomic particles. The conflict between these two theories, quantum mechanics and general relativity, has been one of modern physics' greatest challenges. The findings from 3I/ATLAS suggests that the force revealed by the anomaly may operate on both large and small scales, possibly bridging the gap between these two theories. If this new force is linked to quantum gravitational phenomena, it could represent the long-sought unification of general relativity and quantum mechanics. This would be a groundbreaking development in physics, providing the first concrete evidence that a single theory of everything might be within reach. Yet, the implications go further. If general relativity is only part of the story, then the force revealed by 3I/ATLAS could indicate that the laws of physics we rely on aren't as universal as we once thought. Could gravity, as Einstein described it, be a limited approximation of a much broader, more complex set of interactions? If so, our understanding of the cosmos would need a major revision. Not only would we need to overhaul our models of space-time and gravity, but we may also have to reconsider our entire approach to the universe itself. There's also the possibility that the 3I/ATLAS anomaly points to a deeper truth, a force that transcends both gravity and quantum mechanics. If so, it could usher in a new era in physics, where the boundaries between the known and unknown begin to blur. Imagine a force that can influence space-time in ways we can't yet comprehend, opening up new questions about the very fabric of reality. Could this force be the key to unlocking the mysteries of dark matter, dark energy, or the strange behaviors of distant galaxies? Could it provide the breakthrough needed to understand the universe at the most fundamental level? One thing is certain: 3I/ATLAS has not just raised new questions, it has illuminated an entirely new pathway for exploration. What we thought we knew about gravity, space, and time may soon be revised as scientists continue to peel back the layers of this profound discovery. As we journey deeper into the mystery of this anomaly, the road ahead promises to be as mysterious and transformative as the universe itself. The discovery of a force that seemingly defies gravity raises profound questions not only about the fabric of space-time, but also about the smallest building blocks of the universe, those governed by quantum mechanics. For decades, scientists have sought a theory of quantum gravity to reconcile the world of the very small with the cosmos at large. The 3I/ATLAS anomaly, by hinting at a force capable of bypassing the traditional workings of gravity, could be the breakthrough that connects these two seemingly disparate realms. Quantum mechanics, the theory that describes the behavior of subatomic particles, operates under a different set of rules compared to the smooth, predictable behavior of gravity described by general relativity. Gravity is often viewed as a continuous force, bending space-time in a predictable manner, while quantum mechanics is unpredictable, discrete, and counterintuitive. Particles exist in states of probability, governed by principles like superposition and entanglement, phenomena difficult to reconcile with the continuous curvature of space-time that gravity suggests. The 3I/ATLAS anomaly, which challenges the very idea of gravity's influence, may be the key to understanding how quantum mechanics and general relativity could be brought together. If this force operates across cosmic distances and can manipulate space-time, it could suggest that quantum phenomena are influencing the large-scale structure of the universe in ways we haven't understood. The laws of the quantum world, long confined to particles, might be leaking into space-time, altering how gravity functions on a cosmic scale. One leading theory that could explain this relationship is quantum gravity, a framework that seeks to describe gravity using quantum mechanics. Quantum gravity is still in its infancy, with several competing theories trying to bridge the gap between quantum mechanics and general relativity. Among them is string theory, which posits that fundamental particles are tiny vibrating strings rather than point-like objects. These strings could potentially explain the force that defies gravity by introducing additional dimensions beyond the familiar three. String theory, while elegant, remains speculative due to the lack of experimental evidence until now. The 3I/ATLAS discovery could provide the evidence needed to push string theory and other quantum gravity models into the realm of testable science. If this anomaly is confirmed to arise from quantum gravitational effects, it would be the first experimental validation of ideas that have been purely theoretical. Such a breakthrough would not only challenge our understanding of gravity, but could also validate string theory's predictions of hidden dimensions and forces beyond our current knowledge. Another possibility is that the force revealed by 3I/ATLAS ATLAS could be related to quantum entanglement, a phenomenon where two particles can instantaneously influence each other, regardless of distance. Could the anomaly be an example of entanglement operating on a cosmic scale? If so, it would represent an extraordinary extension of quantum principles into space-time itself. Quantum entanglement, which Einstein famously called spooky action at a distance, might provide the mechanism by which this new force interacts with space-time, manipulating gravitational waves in previously impossible ways. There is also the concept of dark energy, which is thought to be a quantum phenomenon responsible for the accelerated expansion of the universe. Dark energy, much like quantum forces, operates on a mysterious, unseen level, influencing the universe in ways we cannot directly observe. Could the force detected by 3I/A TLAS be an interaction between dark energy and gravitational waves, a result of quantum fluctuations we've only begun to comprehend? If dark energy is a quantum phenomenon, the anomaly could represent a quantum interaction between dark energy and gravity, helping to explain the accelerating expansion of the universe. These ideas are speculative, but they highlight the incredible potential of this discovery. The 3I/ATLAS anomaly could be the gateway to a new understanding of the universe, where quantum mechanics and general relativity are no longer distinct fields, but instead intertwined. This could lead to a unified theory of physics, one that explains everything from subatomic particles to the large-scale structure of the cosmos. However, the road ahead is filled with uncertainties. While the data gathered so far is tantalizing, it is far from conclusive. Theories must be tested, refined, and examined with an open mind. Is this anomaly truly a quantum phenomenon, or is there another explanation yet to be discovered? Are we on the verge of a revolution in physics, or is this simply an unanticipated fluke in the data? For now, the implications of this discovery remain vast and profound. What we once thought of as immutable laws governing gravity and space-time are now being questioned in ways unimaginable just a few months ago. The true nature of the 3I/ATLAS anomaly could unlock answers to the greatest mysteries in science, including the nature of dark matter, the behavior of black holes, and even the ultimate fate of the universe. One of the most perplexing aspects of the 3I/ATLAS anomaly is not just the force it reveals, but the shadow it casts on our understanding of space-time. A force that actively interacts with gravitational waves and seemingly manipulates the fabric of space-time suggests a deeper, unseen interaction beneath the surface of what we perceive. It's as if the universe has a hidden dimension, or force influencing events we cannot directly observe, but can detect through its effects. This shadow is not metaphorical, but a real anomaly, whose effects can be measured by the 3I/ATLAS team using sensitive instruments. The term shadow refers to a force or event that interacts with visible phenomena, in this case, gravitational waves, without being directly visible. Essentially, it's as though something is influencing space-time from an unseen realm. Just as a shadow gives hints about an object's shape without revealing it, this force offers clues about the universe's mechanisms without showing us its true nature. The data from 3I/ATLAS suggests the anomaly doesn't just affect gravitational waves but also influences their path, causing them to behave unexpectedly. Gravitational waves typically follow well-established paths dictated by the curvature of space-time caused by massive objects. However, the anomaly alters these paths, as if a hidden force is tugging at them, bending them in impossible ways. The wave's behavior becomes distorted, an effect akin to the bending of light around a black hole, except it's happening with space itself. This is where the shadow effect comes into play. The anomaly may represent a force acting on space-time from a hidden dimension, one we have no direct access to. The gravitational waves might be distorted due to interactions with another dimension, or a field operating independently of the four dimensions we experience. In essence, space-time may be under the influence of a force or dimension we haven't discovered yet. The shadow could also point to extra dimensions, theorized but never proven. According to string theory and related models, the universe may have more than the four dimensions we experience. These extra dimensions, though not observable, could profoundly affect how we perceive gravity, space, and time. If the 3I/ATLAS anomaly is tied to these dimensions, it would be a confirmation of these long-held but unproven theories. This hidden influence may also help explain phenomena in distant galaxies. For example, scientists have long struggled to explain galaxy movements that don't align with general relativity predictions, particularly in rotation curves. These curves show galaxies rotating faster than they should based on visible matter, suggesting an unseen force. Could this force be the one detected by 3I/ATLAS? If this shadow force affects gravitational waves, it may also explain galaxy rotation anomalies and aspects of dark matter, which exerts gravitational influence but remains unseen. Another critical aspect of this shadow force is its ability to act without apparent mass. Unlike traditional gravitational forces based on mass, this anomaly doesn't seem to require mass to influence space-time. This opens the door to a new way of thinking about forces in the universe. Could this shadow force be massless, like light, yet still exert influence on space-time? If so, it would challenge our understanding of forces traditionally thought to rely on mass, charge, or energy. In cosmology, the implications are immense. If this shadow effect operates universally, it could affect everything from galaxy formation to the expansion of the universe. The force detected by 3I/ATLAS might be responsible for structural phenomena in the universe we don't fully understand. It could even explain why the universe is expanding at an accelerating rate, a mystery that has puzzled scientists for years. Could this shadow force influence the dynamics of dark energy, the substance thought to drive this acceleration? Equally fascinating is the idea that the shadow effect may not be constant. It could vary in intensity, perhaps influenced by cosmic events or structures, such as supermassive black holes or galaxy clusters that we are just beginning to explore. Could the strength of this unseen force fluctuate, revealing itself more strongly in certain places or during specific events? If the shadow force is variable, it would add another layer of complexity to our understanding of the universe. As scientists continue to analyze the data, one of the main challenges will be tracking this force's behavior over time and across space. If this shadow force is key to understanding the anomalies detected by 3I/ATLAS, the next phase of research will involve exploring its properties in detail. What are its limits? What triggers it? And most importantly, how can we study a force that exists in such a way that we can only detect its effects indirectly? As research continues, the shadow effect may reveal itself in ways we cannot yet imagine. And as scientists begin to peel back the layers of this complex force, we may unlock some of the deepest mysteries of the cosmos, ones that have eluded us for centuries. The detection of gravitational waves has been one of the greatest achievements of modern science, confirming a key prediction of Einstein's theory of general relativity. Since the first observation in 2015, scientists have used gravitational waves to probe extreme phenomena, from black hole mergers to neutron star births. These waves are ripples in space-time, caused by the acceleration of massive objects. However, the recent discovery of the 3I/ATLAS anomaly suggests that gravitational waves may not be as simple and predictable as once thought. The anomaly detected by 3I/ATLAS has forced scientists to reconsider how gravitational waves behave. Traditionally, gravitational waves are detected when they pass through Earth, stretching and compressing space-time as they do. The shape and frequency of these waves are determined by the mass and movement of the objects creating them, such as colliding black holes or supernova explosions. These waves offer a direct way to observe violent and distant events in space. But the 3I/ATLAS anomaly suggests that gravitational waves do not always follow expected patterns. Instead of behaving as Einstein's equations predict, these waves bend, twist, and stretch in ways that defy any known gravitational event. The anomaly disrupts the otherwise smooth propagation of the waves, making them appear manipulated by an external force. This raises a crucial question. Could gravitational waves be influenced by a force outside of the known gravitational field? One of the most compelling aspects of this discovery is that the anomaly does not just defy gravity, it also interferes with the fundamental properties of gravitational waves. This force seems to interact with space-time in a way that is different from anything observed before. It doesn't just affect the waves as they pass through space, it seems to alter the very nature of gravitational waves, distorting them in ways that current models cannot anticipate. For physicists, this presents an exciting opportunity but also a significant challenge. Gravitational wave astronomy, which has provided insights into the universe's most extreme phenomena, is based on the assumption that gravitational waves follow predictable patterns. If this anomaly can alter those patterns, the entire approach to gravitational wave detection may need to be reconsidered. It could mean that entire categories of cosmic events or phenomena have been overlooked, events that don't produce gravitational waves in the expected way. But why would this force, this shadow force, affect gravitational waves? One possibility is that the 3I/ATLAS anomaly acts like a cosmic lens, bending and distorting waves as they travel across space. Just as a gravitational lens bends light around a massive object, perhaps this force alters the trajectory of gravitational waves, making them shift in ways that current models cannot explain. This idea would suggest that the shadow force is not just affecting the waves themselves, but also how they propagate across the universe, potentially altering detection methods and how we interpret them. Alternatively, this discovery might indicate that gravitational waves themselves are part of a larger, more complex system, one involving other forces or phenomena we have yet to fully understand. Could gravitational waves simply be a symptom of something deeper, something operating at the most fundamental levels of the universe? The interaction between gravitational waves and the 3I/ATLAS anomaly could be a clue that we need to view gravity and space-time through a radically different lens. As scientists continue to study the data, the behavior of gravitational waves will be one of the most critical aspects of the investigation. New theoretical models will be needed to account for the unexpected distortions caused by the anomaly. Just as gravitational wave detection opened a new window into the universe, the study of these new wave behaviors could offer deeper insights into the true nature of space, time, and the forces that shape the cosmos. Most importantly, this discovery challenges a fundamental assumption of gravitational wave astronomy, that gravitational waves travel freely through space without interference. Could the 3I/ATLAS anomaly signal that the universe's most fundamental forces, those governing space, time, and gravity, are more interconnected and intricate than we ever imagined? As research continues, it will become clearer whether these strange behaviors result from a previously unknown force, or whether they indicate something even more fundamental, a deeper, universal law governing gravity itself. Whatever the outcome, the 3I/ATLAS discovery promises to reshape the field of gravitational wave astronomy, offering a deeper and more profound understanding of the forces at play in the universe. The 3I/ATLAS anomaly continues to puzzle researchers, raising the question of whether this phenomenon is a unique event or a more fundamental feature of the cosmos. Detected in a distant galaxy over 1.2 billion light-years away, the anomaly's reach raises intriguing questions. If such an effect can be observed across vast distances, could this force be universal in scope? Could what we are witnessing be just the first glimpse of a much larger, pervasive phenomenon? In many ways, the detection of this anomaly feels like a cosmic revelation, a discovery that forces scientists to rethink everything, from the laws of gravity to the very structure of the universe itself. The fact that this anomaly was observed from such a distant location suggests it may not be a localized event. If this force is active across such vast expanses of space, its reach could be far greater than we realize, potentially acting as a constant underlying presence in the fabric of the universe. Initially, scientists believed gravitational anomalies were rare, tied to specific cosmic events like black hole collisions or supernova collapses, but the 3I/ATLAS anomaly does not conform to these expectations, suggesting there may be a more ubiquitous force at work, one that interacts with space-time in ways we have yet to fully understand. This challenges the very notion of space-time as a passive backdrop for cosmic events. Could space-time itself be active, shaped by an unseen force that we have not yet identified? The implications are vast, and as researchers investigate further, they're finding that the 3I/ATLAS discovery may only be the tip of the iceberg. Previous studies of galaxy clusters and the cosmic microwave background CMB have hinted at unexplained distortions in space-time. Could these distortions be another manifestation of this universal force? If present throughout the universe, could it explain some of the strange behaviors we observe in galaxies, galaxy clusters, or even the expanding universe? Consider the accelerating expansion of the universe a profound mystery in cosmology. For decades, scientists have struggled to understand why the expansion of the universe is speeding up rather than slowing down due to gravitational attraction. This phenomenon has been attributed to dark energy, a mysterious force thought to push galaxies apart. Could the 3I/ATLAS anomaly be partly responsible for this acceleration? Might the force detected in distant gravitational waves be linked to dark energy, or share properties that influence the rate at which the universe expands? The large-scale structure of the universe, shaped by gravity, could also be explained by the anomaly. The 3I/ATLAS discovery might help explain why certain cosmic structures, such as galaxy clusters and superclusters, behave in unexpected ways. This force could act differently in various regions of space, creating variations in the behavior of matter and energy that lead to the formation of the universe's largest structures. What we once considered random quirks of space may, in fact, be manifestations of a deeper, universal law at work. Another possibility is that the anomaly ties into cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. Cosmic inflation is believed to have been driven by energy that exerted an outward force on the universe, causing it to expand exponentially. Could the 3I/ATLAS anomaly represent a new type of inflationary force, one that operates on a more subtle, large-scale level, continuously influencing the expansion of the universe long after the initial inflationary period? Studying a phenomenon as vast and fundamental as this anomaly presents challenges, as its effects are subtle and difficult to detect. While gravitational waves offer a unique window into the universe, the influence of this force may only be detectable under specific conditions or across vast distances. To understand its nature and implications, scientists will need to develop new observation techniques, many of which may not yet exist. This discovery is significant because it forces us to ask fundamental questions about the universe itself, questions that challenge our current models of space-time and gravity. If this force is universal, it could rewrite the fundamental laws of physics and potentially offer answers to some of the universe's greatest mysteries, including the nature of dark energy, the behavior of black holes, and cosmic acceleration. As researchers delve deeper into this phenomenon, a critical question will be whether the anomaly represents a universal force or a localized event. If it is universal, it could imply that the fabric of the universe is not as stable as we once thought. The forces shaping the cosmos may be more complex, intertwined, and mysterious than we ever imagined. In the years ahead, as the investigation into the 3I/ATLAS anomaly intensifies, the field of physics may undergo a fundamental shift. The search for new theories to explain this phenomenon will likely lead to the development of new scientific models that could change our understanding of the universe and our place within it forever. As the investigation into the 3I/ATLAS anomaly deepens, one fundamental question arises: what unseen forces are at work behind this phenomenon? Gravity, as we know it, has been a cornerstone of our understanding of the cosmos. However, this anomaly challenges that foundation, suggesting the existence of hidden forces that operate beneath the surface of known physical laws. Could these forces be responsible for the observed irregularities in space-time? The first step in understanding these unseen forces is to reconsider what we know, or thought we knew, about the universe. For centuries, we've understood that the four known forces — gravitational, electromagnetic, strong nuclear, and weak nuclear — govern all matter and energy. These forces form the basis of modern physics. But what if the universe is governed by forces beyond these known interactions? At the heart of this anomaly, there appears to be an influence that doesn't fit neatly into the categories of any known force. If this force is tied to the 3I/ATLAS anomaly, it suggests the existence of a hidden force that interacts with space-time in ways current models cannot explain. Could this force be something entirely new? Or could it be a previously unknown aspect of one of the existing forces, operating in ways we haven't yet understood? To explore this, we must consider that the 3I/ATLAS anomaly could be the first observable clue that there are more forces in the universe than we currently recognize. Just as dark matter, undetectable by light, was once unknown and detectable only through its gravitational effects, these unseen forces may influence the cosmos without direct evidence of their presence. Rather than being detectable through traditional observation, they might manifest subtly, challenging the very structure of space-time itself. One compelling possibility is that the anomaly could be linked to dark energy, the mysterious force believed to be responsible for the accelerated expansion of the universe. Dark energy accounts for about 68% of the universe's total energy content, but its true nature remains elusive. It is understood as a repulsive force, pushing galaxies apart. Could the 3I/A TLAS anomaly be a manifestation of dark energy acting on a cosmic scale to distort gravitational waves in space-time? If this force influences space-time in ways that defy gravity, it could provide a crucial link between dark energy and the more familiar forces of physics. Another intriguing possibility is that the anomaly could relate to dark matter, which interacts through gravity but not through electromagnetic radiation, making it invisible to our instruments. Though dark matter constitutes about 27% of the universe's mass, it cannot be directly detected by traditional methods. However, it is believed to exert gravitational effects on visible matter, influencing the motion of galaxies. Could the 3I/ATLAS anomaly represent an interaction between dark matter and gravitational waves, offering a new way to study dark matter and its gravitational effects? Perhaps the anomaly is even more exotic, an entirely new form of energy, unlike anything we've encountered before. Some physicists speculate about the existence of quintessence, a hypothetical energy that evolves over time and could account for the accelerated expansion of the universe. Quintessence differs from dark energy in that it evolves as the universe does. Could the 3I/ATLAS anomaly be a signal of quintessence, a dynamic force whose effects on space-time have only recently become detectable? There is also the possibility that the anomaly is linked to modifications of gravity. While Einstein's general relativity has been foundational in modern gravitational theory, higher-order corrections to these equations might become apparent under extreme conditions or over vast cosmic distances. These corrections could represent a more complex form of gravity that operates differently than classical theory predicts. Could the 3I/ATLAS anomaly provide the first evidence of such gravitational modifications, offering a new understanding of gravity on large scales? Alternatively, the anomaly could relate to extra dimensions, hidden spatial dimensions beyond the familiar 3 dimensions of space and 1 of time. Theoretical models, such as string theory, suggest the universe may contain extra spatial dimensions that are inaccessible to us under normal conditions. These extra dimensions could profoundly influence the forces of nature, potentially explaining the strange behavior of gravitational waves detected by 3I/ATLAS. Could this anomaly signal interactions between our observable universe and these extra dimensions, distorting space-time in ways we cannot directly observe? Each of these possibilities represents a different facet of the mystery surrounding the 3I/ATLAS anomaly. But one thing is clear: whatever the unseen force is, it is not only influencing gravitational waves and space-time, but could also be affecting the way we perceive the universe. This anomaly opens new avenues for exploration, potentially leading us beyond known forces into a realm of physics, where space and time are more fluid and dynamic than ever imagined. As scientists continue to study this phenomenon, the search for these unseen forces will drive new experiments, theories, and discoveries. Whether we uncover a new fundamental force, or simply witness the earliest glimpses of a deeper truth, the 3I/ATLAS anomaly promises to be one of the most transformative discoveries in the history of physics. As the study of the 3I/ATLAS anomaly progresses, one theory is gaining traction: the possibility that the force observed is linked to extra dimensions, hidden realms beyond the familiar 3 dimensions of space and 1 of time. The concept of extra dimensions isn't new. It's been proposed in advanced theories like string theory and brane cosmology. But could the 3I/ATLAS anomaly, which defies known forces, offer a glimpse into these unseen dimensions? For decades, scientists have speculated about higher spatial dimensions that exist beyond our perception. These extra dimensions would not be visible to the naked eye and would not affect our daily lives. However, the possibility that they influence physical phenomena and even shape space-time has become a key area of study in modern theoretical physics. Could the 3I/ATLAS anomaly be the first evidence of these dimensions interacting with the observable universe? To understand this, we need to explore the idea of extra dimensions. In string theory, one of the leading frameworks to reconcile quantum mechanics with general relativity, the universe is said to consist of more than the 4 dimensions we observe. String theory suggests that there could be 9 spatial dimensions. These dimensions are thought to be compactified on a microscopic scale, invisible to us, but they could profoundly affect the fundamental forces, including gravity. String theory posits that particles are not point-like objects, but tiny vibrating strings. How these strings vibrate depends on the dimensions they exist in. The arrangement of extra dimensions could influence the behavior of fundamental forces like gravity. The 3I/ATLAS anomaly, which distorts gravitational waves in ways general relativity cannot explain, could be evidence that extra dimensions are interacting with our universe. The anomaly might be a leak from these extra dimensions, affecting space-time in ways previously unknown. Mathematical models suggest that the effects of extra dimensions wouldn't be noticeable at everyday scales but might appear in extreme conditions, like the detection of gravitational waves from distant galaxies. If the 3I/ATLAS anomaly is tied to extra dimensions, it would represent the first tangible evidence that the universe is far more complex than we've realized, shaped not just by the 4 observable dimensions, but by a hidden network of extra dimensions influencing gravity. Another relevant theory is brane cosmology, which proposes that the universe isn't just a 4-dimensional space-time continuum, but a 3-dimensional brane within a higher dimensional space. In this model, the forces we experience, including gravity, could result from interactions between our brain and the higher dimensional space around it. The 3I/ATLAS anomaly might represent a disturbance in this higher dimensional space, influencing gravitational waves and space-time. If true, gravity may not just curve space-time within our universe, but could interact with other dimensions. Although speculative, these ideas offer exciting avenues for future research. The anomaly detected by 3I/ATLAS might be the first sign of higher dimensional forces at work. The way gravitational waves behave, rejecting known spacetime rules, suggests that we are dealing with something beyond our current understanding, possibly tied to a hidden, complex network of dimensions. The potential of extra dimensions is immense. If they exist and influence the forces of nature, they could help solve many of the universe's mysteries. Could extra dimensions explain dark matter and dark energy, substances that make up most of the universe's mass and energy, but remain undetectable by conventional means? If the 3I/ATLAS anomaly is connected to these forces, it could offer new insights into these cosmic mysteries, potentially providing a better understanding of the fundamental forces shaping the universe. This discovery could also revolutionize our understanding of space-time and reality itself. Proving the existence of extra dimensions would validate some of the most ambitious theories in modern physics. It could pave the way for breakthroughs in energy generation, faster than light travel, and even manipulating the fabric of space-time. However, we are still far from fully understanding the nature of this force or dimension. The 3I/ATLAS anomaly may only be the beginning. It could take years, even decades, to develop the necessary tools and technologies to study higher dimensional interactions. But the possibility of discovering hidden dimensions in the universe presents one of the most exciting frontiers in physics. The 3I/ATLAS discovery could open a new chapter in the exploration of the cosmos, one where the boundaries between dimensions are more fluid than we once thought. We are standing at the threshold of a new era in physics, one that could forever change our understanding of the universe. As the study of the 3I/ATLAS anomaly deepens, one critical question stands out. What exactly are the unseen forces behind this phenomenon? Gravity, as we know it, has been a fundamental pillar of our understanding of the cosmos, but this anomaly challenges that foundation. It suggests there are hidden forces at work, forces that don't behave according to traditional expectations, operating beneath the surface of known physical laws. Could these forces explain the observed irregularities in space-time? The first step in understanding this anomaly was to reconsider what we thought we knew about how the universe operates. For centuries, we've understood that the known forces, gravitational, electromagnetic, strong nuclear and weak nuclear, govern matter and energy. These 4 forces have been the foundation of modern physics. But what if there are forces beyond these known interactions? At the core of this anomaly, there seems to be an influence that doesn't fit into the categories of any known force. If the force behind 3I/ATLAS is related to this anomaly, it suggests a hidden force interacting with spacetime in ways that cannot be explained by current models. Could this force be something entirely new, or a previously unknown aspect of one of the existing forces operating in ways we don't yet understand? To explore this, researchers considered that the 3I/ATLAS anomaly could be the first observable clue that there are more forces in the universe than we recognize. Much like dark matter, detected only through its gravitational effects, these unseen forces may influence the cosmos without leaving direct evidence. Rather than being detectable through conventional observation, they may manifest subtly, challenging our understanding of spacetime itself. One compelling possibility is that the anomaly could be related to dark energy, the mysterious force believed to be responsible for the accelerated expansion of the universe. Dark energy, which makes up about 68% of the universe's total energy, is understood as a repulsive force pushing galaxies apart. Could the 3I/ATLAS anomaly be a manifestation of dark energy affecting space-time and gravitational waves on a cosmic scale? If this force influences space-time in ways that defy gravity, it could be a crucial link between dark energy and other known forces. Another possibility is that the anomaly is connected to dark matter, which interacts through gravity but not through electromagnetic radiation, making it undetectable by traditional instruments. While dark matter constitutes about 27% of the universe's mass, it exerts gravitational effects on visible matter, influencing the motion of galaxies. Could the 3I/ATLAS anomaly represent an interaction between dark matter and gravitational waves, providing new insights into the nature of dark matter? Perhaps this anomaly is even more exotic, an entirely new form of energy, unlike anything we've encountered. Some physicists speculate about quintessence, a hypothetical energy that evolves over time and could account for the accelerated expansion of the universe. Unlike dark energy, quintessence would change as the universe evolves. Could the 3I/ATLAS anomaly signal this type of energy, offering a new understanding of cosmic expansion? Another consideration is gravitational modifications. While Einstein's general relativity has been the cornerstone of gravitational theory, higher-order corrections to these equations might only be apparent under extreme conditions or across vast cosmic distances. Could the 3I/ATLAS anomaly provide the first evidence of such gravitational modifications, offering a more nuanced understanding of gravity's behavior on large scales? Alternatively, the anomaly could be tied to extra dimensions, hidden spatial dimensions beyond the familiar 3 dimensions of space and 1 of time. Theoretical models, such as string theory and brane cosmology, suggest that the universe could contain extra dimensions. These dimensions could influence the forces of nature, possibly explaining the unusual behavior of gravitational waves detected by 3I/ATLAS. Could this anomaly be the result of interactions between our universe and these extra dimensions, distorting space-time in ways we cannot directly observe? Each of these possibilities represents a different facet of the mystery surrounding the 3I/ATLAS anomaly. But one thing is clear: whatever the unseen force is, it is not only affecting gravitational waves and space-time, but could also be influencing how we perceive the universe. This anomaly opens new avenues for exploration that could take us beyond known forces and into a realm of physics where space and time are more fluid and dynamic than ever imagined. As scientists continue to analyze this phenomenon, new theoretical and experimental approaches will be necessary. The anomaly presents an exciting opportunity for physicists to challenge their assumptions and expand their understanding of the universe. By studying this force and its interaction with gravitational waves, researchers have the chance to uncover an entirely new layer of the cosmos, one previously hidden from view. The implications for space-time, gravity, and the fundamental forces of nature are enormous, and this discovery could mark the beginning of a scientific revolution. The future of this research holds the potential for groundbreaking discoveries that could reshape our understanding of the universe, forever altering how we perceive the cosmos itself. As the study of the 3I/ATLAS anomaly unfolds, it raises profound philosophical questions about the nature of the universe and humanity's place within it. The anomaly challenges the bedrock laws of physics, forcing us to reconsider fundamental assumptions about the cosmos. For centuries, science has uncovered hidden layers of reality, but with this discovery, we may be standing on the cusp of a paradigm-shifting moment, one that asks not only what is, but what could be. At its core, the anomaly confronts the limits of human knowledge. Despite our advancements in understanding space, time, and the forces of nature, there are still unknowns that defy explanation. Science has long been driven by the belief that, with enough time, observation, and experimentation, all mysteries can be solved. But the 3I/ATLAS anomaly challenges this ideal. Are there aspects of the universe that remain beyond our grasp? Could there be forces or dimensions of reality that are imperceptible to the tools of human inquiry? If so, how should we rethink our role as observers and explorers of the universe? The discovery of a force that appears to bypass known laws of physics introduces questions not only about science, but about human understanding itself. How do we reconcile our growing ability to explore the far reaches of space with the growing realization that we may only be scratching the surface of what is possible? The anomaly suggests that the universe is more mysterious and unfathomable than we have ever imagined. Could the forces we think we understand, like gravity, be mere reflections of something deeper, waiting to be uncovered? The philosophical implications extend beyond the nature of the universe. The discovery of this unknown force forces us to confront larger questions about the meaning of existence. If the laws of physics, once believed to be immutable and universal, can be bent or broken by a force we cannot explain, what does that say about the nature of reality? Are we truly living in a universe governed by consistent, unchanging laws, or are we participants in a much more chaotic, complex and unpredictable reality than we thought? The 3I/ATLAS anomaly also raises important questions about our future. If this newfound force proves to be as revolutionary as it appears, the implications could be far-reaching, not just for physics but for all aspects of human civilization. Could the discovery of this new force lead to new technologies that radically change our way of life? Could we learn to harness this force to manipulate space-time itself? The potential for such breakthroughs is staggering, but they also bring complex ethical and existential questions. How should we use such knowledge? And who decides how it's applied? Should humanity, with all its potential for good and ill, have the power to manipulate the very fabric of space and time? As with many great scientific discoveries, the philosophical implications are vast and they are not easily resolved. The question of what lies beyond known forces and dimensions may take centuries to fully answer, if it is answerable at all. Yet this discovery reminds us of the humbling nature of human knowledge. Despite our technological advancements, we are still confronted with mysteries that defy explanation. The more we uncover, the more we realize how little we truly understand. There is also a deeper philosophical question at play. Does the discovery of something beyond our understanding mean that we've reached the limits of human knowledge? Or does it mark the beginning of a new era where the unknown becomes the subject of study? Some argue that each mystery solved only leads to more questions, suggesting that our journey of discovery is endless, a continual process of expanding our comprehension of the universe. The 3I/ATLAS anomaly might just be the latest example of this eternal cycle. On an existential level, the discovery of a force that defies known laws raises questions about our place in the cosmos. For centuries, humanity has sought to understand the universe, often placing itself at the center of that understanding. But what happens when we encounter a force or phenomenon that seems to exist beyond our comprehension or experience? What does that say about humanity's role in the grand scheme? Are we the masters of this universe, as we once imagined, or are we merely one small part of a much larger, more mysterious reality? The 3I/ATLAS anomaly serves as a poignant reminder of the limits of human perception. Despite our scientific advancements, there will always be aspects of the universe that elude us. The search for answers to the anomaly may lead to the discovery of deeper layers of the cosmos, but it may also lead to the realization that the universe, in its infinite complexity, may never be fully understood. Perhaps, in itself, that is one of the most profound discoveries. As we continue to probe the mysteries of the universe, philosophical and existential questions will inevitably intertwine with those of physics. The 3I/ATLAS anomaly is not just a scientific mystery, it is a window into the unknown, challenging our assumptions about reality itself. The answers we seek may forever change how we view the universe, and ultimately how we view ourselves, the 3I/AATLAS anomaly has sparked a cascade of questions and research, transforming our understanding of the universe. As scientists continue to analyse this discovery, it's becoming clear that we stand at the edge of a new frontier, one that could redefine everything we know about space, time, and the fundamental forces of nature. This is a frontier that challenges the limits of human knowledge and beckons us into uncharted territory. But where do we go from here, and what does the future hold for the exploration of the unknown? The discovery of the 3I/ATLAS anomaly has opened a new era of scientific exploration, one where the very rules of the universe are up for debate. Traditional physics models, which have served as the foundation of scientific progress for centuries, are now being questioned. This anomaly has sparked a paradigm shift, challenging our assumptions about gravity, space-time, and even the nature of reality itself. A force interacting with gravitational waves in ways that defy known laws of physics has sparked a revolution in fundamental physics, cosmology, and technology. As scientists work tirelessly to gather data and develop new theories, the implications of this discovery are already being felt across many fields. Researchers from astrophysics, quantum mechanics, cosmology, and theoretical physics are collaborating in unprecedented ways to study the anomaly and understand its nature. This cross-disciplinary collaboration exemplifies the new frontier, one where no single field holds all the answers, and where merging knowledge from different domains is essential to uncovering the mysteries of the universe. The potential for new discoveries is immense. The 3I/ATLAS anomaly could hold the key to understanding some of the most elusive aspects of cosmology, such as the nature of dark matter and dark energy. Dark matter makes up about 27% of the universe and exerts gravitational effects, yet does not emit detectable radiation. Similarly, dark energy, which is believed to drive the accelerated expansion of the universe, remains mysterious. Could the force revealed by 3I/ATLAS be a hidden link between these enigmatic substances? If so, it could revolutionize our understanding of the universe's composition and expansion. The anomaly may also offer insights into black holes and space-time behavior near these extreme objects. Black holes remain enigmatic, with many unanswered questions about their internal structure or their interaction with surrounding space-time. Could the 3I/ATLAS anomaly offer clues about these unknown realms? If the anomaly is connected to gravitational waves, it might provide a glimpse into the inner workings of black holes or other extreme phenomena. The implications extend beyond cosmology into the realm of technology. Understanding how this unknown force interacts with space-time could lead to advancements in energy generation, propulsion, and even the manipulation of space itself. Imagine harnessing this force to create new forms of energy or to develop faster-than-light travel. While this may sound like science fiction, history has shown that revolutionary discoveries often lead to technological breakthroughs that once seemed impossible. As research progresses, one of the key questions will be how to measure and manipulate this force. If it does indeed influence space-time, understanding how to control it could unlock new ways to interact with the very fabric of the universe. The idea of altering space-time, whether for communication, travel, or energy, opens up a vast range of possibilities. While we're still far from fully understanding the anomaly, the potential for future technological breakthroughs is an exciting prospect for generations of scientists and innovators. Beyond the scientific and technological implications, the discovery also brings with it a philosophical and cultural awakening. The idea that the universe is not governed by simple, predictable laws, but by forces that can be bent or bypassed, challenges our perceptions of reality. As we uncover more, we realize how little we truly understand. The 3I/ATLAS anomaly reminds us that we are only beginning to grasp the complexity of the universe. The more we uncover, the more we realize how much remains unknown. This anomaly also forces us to reconsider humanity's place in the grand scheme of things. For centuries, we have looked to the stars with curiosity, often placing ourselves at the center of understanding. But what happens when we encounter a force beyond our comprehension? What does it say about humanity's role in the grand order of the cosmos? Are we the masters of this universe as once imagined, or are we just a small part of a far larger, more mysterious reality? The 3I/ATLAS anomaly serves as a reminder of the limits of human perception. Despite our scientific progress, there are always aspects of the universe that elude us. The search for answers may lead to deeper layers of the cosmos, but it may also reveal that the universe's infinite complexity may never be fully understood. In itself, this could be one of the most profound discoveries of all. As we continue to explore the mysteries of the universe, questions of philosophy and humanity's place will intertwine with physics. The 3I/ATLAS anomaly is not just a scientific mystery, it's a window into the unknown, challenging our assumptions about reality itself. The answers we seek may forever change how we view the universe, and ultimately how we view ourselves. The 3I/ATLAS anomaly has sparked a cascade of new questions and research, transforming our understanding of the universe. As scientists continue to analyze this discovery, it's clear that we are standing at the edge of a new frontier, one that could redefine space, time, and the fundamental forces of nature. This discovery pushes the boundaries of human knowledge, beckoning us into uncharted territory. What comes next will depend on further research, theory, and technological innovation. But one thing is certain: the 3I/ATLAS anomaly will alter the course of physics, cosmology, and possibly human existence. The anomaly is not just a scientific discovery, it marks the beginning of a new chapter in humanity's understanding of the universe. Its full impact may take decades, even centuries to fully unfold, but the questions it raises are profound. How will this discovery change our perception of space and time? How will it alter the fundamental laws we've relied on for centuries? And, most importantly, what will we do with this newfound knowledge once we uncover the mystery of this force? The answers may not come quickly, but the pursuit of understanding will drive the scientific community forward. As theories are refined and new technologies developed, more startling revelations are likely to emerge. What we thought we knew about the universe may soon be obsolete, replaced by an entirely new framework. Within this framework, there are bound to be discoveries that stretch the limits of human comprehension. Already, gravitational wave astronomy has entered a new phase. The 3I/ATLAS anomaly has shown that gravitational waves can be influenced in ways previously thought impossible. This could lead to new techniques for detecting hidden forces, exploring deeper realms of space-time, and even observing phenomena once inaccessible to us. It may be the key to unlocking new dimensions, understanding dark energy, or discovering new forms of matter and energy that challenge fundamental physics. The technological implications are profound. If we can understand and harness the forces behind the 3I/ATLAS anomaly, we may see innovations in energy generation, space travel, and communications. The manipulation of space-time, if feasible, could lead to breakthroughs that were once relegated to science fiction. Concepts like faster-than-light travel or controlling gravity may no longer be fantasies, but scientific possibilities waiting to be realized. However, this potential for technological advancement also raises ethical and existential questions. As we push the boundaries of knowledge and power, we must consider the responsibility that comes with it. How should humanity approach the use of such discoveries? What safeguards are needed to ensure these new technologies are used for the greater good and not for destruction or exploitation? As we venture into this new frontier, it's crucial to proceed with caution, mindfulness, and a strong ethical framework, recognizing the power we wield and the potential consequences of our actions. In the long term, the 3I/ATLAS anomaly may not just be a single discovery, but the spark that ignites a broader rethinking of our place in the universe. If this anomaly is tied to hidden dimensions, new forces, or undiscovered aspects of the cosmos, it will force us to confront some of the most profound philosophical and existential questions about reality itself. How does the discovery of forces beyond our understanding reshape our view of the universe? And in turn, how does it redefine humanity's role within it? As we look to the future, the path remains unclear. The answers to these questions will unfold over time, leading to new ways of thinking, new technologies, and new possibilities. The pursuit of knowledge is a journey, and this discovery, like so many before it, reminds us that there is always more to learn, more to explore, and more mysteries to uncover. The universe, with all its complexities and wonders, is an ever-expanding frontier, and the 3I/ATLAS anomaly is just the latest chapter in this ongoing story of exploration. Ultimately, the future is unwritten, but brimming with potential. The discovery of a force that defies gravity, distorts space-time, and challenges the laws of physics is not just a breakthrough for physicists, it is a moment for all humanity. The questions raised by the 3I/A TLAS anomaly touch on our deepest desire to understand the universe, to push beyond the boundaries of what we know, and to envision new futures for science, technology, and society. In this pursuit, we may uncover truths far greater than anything we can yet imagine. As the story of the 3I/A TLAS anomaly unfolds, we stand at the threshold of a new age of discovery. The road ahead is uncertain, but one thing is clear: we are no longer the same. The universe, once a mystery, is now an invitation, a call to continue our journey, to seek the unknown, and to unlock the secrets that lie hidden in the vastness of space. As we continue to probe the mystery of the 3I/A TLAS anomaly, it is increasingly clear that this discovery could reveal the limitations of human perception itself. Throughout history, humanity has prided itself on its ability to understand the natural world, pushing boundaries and expanding the limits of knowledge. But the 3I/A TLAS anomaly forces us to ask, are we truly equipped to grasp the vastness of the universe, or are we forever constrained by our own sensory and cognitive limitations? In this profound moment, we find ourselves questioning the very foundation of human understanding. One of the most compelling aspects of this discovery is the challenge it presents to our perception of reality. Gravitational waves, as we know, are invisible. They stretch and compress space-time in ways that we can't directly see, yet they can be measured through sophisticated technology. But the 3I/A TLAS anomaly goes even further, introducing a force that actively shifts the behavior of space-time and gravitational waves. This raises the question, could it be that our human senses, limited to just a few of the known dimensions, are inherently incapable of perceiving the full complexity of the universe? Could there be forces beyond our immediate awareness that govern the fabric of space-time in ways that our senses cannot detect? For centuries, science has advanced by developing increasingly refined instruments to extend our senses. From the first telescopes that reveal distant stars to the advanced detectors that now allow us to observe gravitational waves, technology has granted us a way to explore realms beyond our immediate experience. Yet, despite these tools, we remain confined by the basic limitations of our sensory apparatus. Could the 3I/A TLAS anomaly be proof that there are phenomena beyond our current understanding of physics, forces that are simply invisible to the human mind, despite being detectable through instrumentation? Could we be confronting a universe that is far more complex than we can comprehend? Theories like extra dimensions and quantum gravity suggest that there are hidden layers of reality beyond the reach of our perception that govern the way the universe operates. As we encounter these ideas more frequently in cutting-edge science, we must confront the fact that the universe is not only far bigger than we imagine, it may also be far more intricate and beyond human comprehension. The 3I/A TLAS anomaly could be the first signal of such a reality, suggesting that what we perceive is only a fraction of the true nature of the universe. It may be that our very perception is just a crude approximation of a vastly richer reality. Moreover, the implications of this anomaly extend beyond the realm of physics. It challenges our philosophical understanding of existence itself. How much of the universe can we truly know? And is knowledge itself even a complete and accurate representation of reality? With each new discovery, we are confronted by the possibility that there are layers of existence we are not yet able to comprehend, or perhaps may never be able to. This realization forces us to rethink the purpose and limits of human exploration. As the scientific community strives to understand this anomaly, the question remains, how much of the universe can we really know? The further we delve into the mysteries of space-time, the more we realize that there are limits to our understanding, not just in terms of knowledge, but in terms of perception itself. The next great challenge for physicists, astronomers, and philosophers alike may be learning to live with these limitations and embracing the unknown as a central element of our quest for discovery. Perhaps, in accepting these limitations, we will come to appreciate the true mystery of the universe, that it may be beyond our ability to fully understand, yet still worthy of our pursuit. The discovery of the 3I/A TLAS anomaly has reignited a long-standing pursuit in physics. the search for a unified theory of everything. For over a century, physicists have sought to reconcile the two great pillars of modern physics, general relativity and quantum mechanics. The anomaly presents an intriguing possibility that could bridge the gap between these two realms of physics, offering new hope that we might finally achieve a unified understanding of the forces that govern the universe. At the heart of this effort lies the challenge of combining the macroscopic view of the universe, governed by general relativity, with the microscopic world of particles and forces as described by quantum mechanics. General relativity, which explains the behavior of large objects like planets, stars, and galaxies, operates within a framework of smooth space-time curvature. Quantum mechanics, on the other hand, describes the behavior of particles on the smaller scales, where things are uncertain, probabilistic, and governed by the strange principles of wave-particle duality and quantum entanglement. These two frameworks, while both successful in their respective domains, seem incompatible. General relativity treats gravity as the curvature of space-time caused by mass, while quantum mechanics deals with particles interacting in probabilistic fields. The 3I/ATLAS anomaly could provide a key to unlocking this divide, revealing how gravity and quantum phenomena might be connected. For example, some theories in quantum gravity suggest that space-time itself might be quantized. That is, it could consist of discrete units, rather than being smooth and continuous as general relativity suggests. If the anomaly is indeed linked to quantum effects on the macroscopic scale, it might reveal how the fabric of space-time operates at both the large and small scales. This could lead to the discovery of a new set of principles that govern the universe, one that incorporates both the smooth curvature of gravity and the probabilistic nature of quantum mechanics. Some scientists are already suggesting that this force detected by the 3I/ATLAS anomaly might be a manifestation of quantum gravitational effects, those that occur when both quantum mechanics and general relativity are at play. If this turns out to be the case, it would represent a major step forward in the search for a unified theory. It could provide experimental evidence for theories like string theory, which posits the existence of extra dimensions and suggests that gravity might emerge from quantum processes at small scales. While this remains speculative, the 3I/ATLAS anomaly could ultimately provide the empirical data needed to support or reject these theories, bringing us closer than ever to the long-sought goal of a theory of everything. The search for such a theory is not just about understanding how the forces of nature work, it's about unraveling the fundamental principles that govern the very structure of reality. One of the most profound implications of the 3I/ATLAS anomaly is the potential for a revised understanding of space-time. Space-time, as described by Einstein's theory of general relativity, is a smooth, four-dimensional continuum that bends in the presence of mass and energy. This understanding has formed the backbone of modern physics for over a century, providing us with insights into everything from the behavior of galaxies to the flow of time itself. However, the 3I/ATLAS anomaly suggests that this concept might be far too simplistic, and that space-time itself may be more malleable and dynamic than previously thought. The anomaly reveals that the normal rules of gravitational wave propagation, the way ripples in space-time travel across the cosmos, are not always adhered to. These waves, which are typically seen as ripples in the fabric of space-time created by massive cosmic events, do not always behave in the manner predicted by current theories. This raises the possibility that space-time itself is subject to influences from unknown forces, which could stretch, contract, or otherwise manipulate its structure in ways that defy conventional wisdom. If true, this would mean that the very foundation of modern physics, our understanding of space-time, could be drastically altered. This possibility that space-time is more dynamic and interactive than we previously imagined could pave the way for new models of the universe. Models that incorporate the anomaly into our understanding of how the cosmos functions. We may need to rethink fundamental concepts, including space-time curvature, gravitational fields, and even the nature of mass itself. Our understanding of how mass interacts with space-time, for instance, could shift, leading us to reconsider the principles of gravity and inertia, and how they govern celestial bodies, black holes, and even the very passage of time. Some theorists have already proposed that space-time might not be a continuous entity, but rather a discrete structure, made up of tiny building blocks that are influenced by unknown forces. This idea, which draws on theories like quantum gravity, is still speculative, but the 3I/ATLAS anomaly might be the first observational evidence of such a phenomenon. If this proves to be the case, it would mark a profound shift in our understanding of how the universe operates, both on macroscopic scales, like the movement of planets, and on microscopic scales where the nature of particles and fundamental forces is still largely unknown. This new model would challenge the well-established idea of a smooth, uninterrupted continuum, suggesting instead that the universe is built from discrete interacting components that are subject to previously unaccounted for forces. Furthermore, this shift in our understanding of space-time could have practical, real-world implications that extend far beyond the realm of theoretical physics. If we can learn to manipulate the fabric of space-time itself, we might unlock entirely new technologies. Advanced propulsion systems for space travel could become a reality, allowing humanity to travel across vast distances in space without the limitations of conventional fuel or time. Such technologies might even lead to the development of new methods of energy generation, tapping into the very structure of space-time to harvest power in ways that we cannot yet fully comprehend. The ability to reshape space-time could one day enable us to create technologies that were once thought to exist only in science fiction. Moreover, the ability to manipulate space-time could have implications for areas such as communication and computing. If we can bend or warp space-time, it might be possible to develop new forms of instantaneous communication, bypassing the limits of distance and time that currently governs how information travels. This could revolutionize everything from global communications to the way we process and store information. Similarly, advances in quantum computing, driven by a deeper understanding of the fabric of space-time, might lead to breakthroughs that could solve problems once thought insurmountable. The journey into this new understanding of space-time has only just begun, and the possibilities it holds are both awe-inspiring and humbling. As researchers continue to explore the 3I/ATLAS anomaly, we may soon find that our current models of the universe are only the beginning. The anomaly might be the first step in uncovering a more intricate and complex understanding of space-time, one that challenges not only the theories we have, but also the limits of human perception and imagination. If the anomaly leads to a deeper understanding of the fabric of the cosmos, it could profoundly reshape our view of the universe and our place within it. The 3I/ATLAS anomaly, in essence, serves as a reminder of the vast unknowns that still remain in the universe. While we have made incredible strides in our understanding of space and time, this discovery signals that there is still much more to explore. Space-time, far from being a static backdrop for the events of the universe, could turn out to be a dynamic and interactive entity that is far more complex and mysterious than we have ever imagined. The exploration of this anomaly is just the beginning of a new chapter in our understanding of the universe, and as we move forward, the questions it raises will continue to challenge our most fundamental assumptions about the nature of reality itself. The 3I/ATLAS anomaly has the potential to spark what could be called a cosmic revolution in both science and philosophy. We stand on the edge of a scientific threshold that could reshape our understanding of everything, from the fundamental nature of reality to humanity's place in the universe. This discovery, which defies long-established laws of physics, is not just a minor correction to our current theories. It's a revolution that could change the course of physics, technology, and even our conceptualization of space, time, and existence. For over a century, humanity has relied on the theories of general relativity and quantum mechanics to explain the complexities of the universe. The breakthrough provided by 3I/ATLAS suggests that these frameworks may not be the full picture. If a new force can interact with space-time in such a way that it bypasses known laws of gravity, it raises the possibility of uncovering a deeper, unified theory of the cosmos, one that explains not only the workings of the large-scale universe, but also the strange, probabilistic behaviors of the quantum world. What we are witnessing may be the dawn of a new scientific paradigm. Throughout history, humanity has undergone periodic revolutions in understanding, from the Copernican revolution, which displaced Earth from the center of the universe, to the quantum revolution, which fundamentally altered our view of the subatomic world. The 3I/ATLAS anomaly could represent the next great leap forward, a revolution that challenges the very fabric of space-time itself, potentially leading to a unified theory of the forces that govern all of existence. At the heart of this revolution is a fundamental shift in how we perceive the universe. If this anomaly represents a new force or a deeper interaction between dimensions, it implies that the universe is far more complex than we can currently comprehend. The discovery challenges us to rethink our place in the cosmos. For centuries, we've considered the laws of physics to be universal, immutable truths that govern everything from the motion of the planets to the formation of galaxies. Now, we face the possibility that these laws may not be as unchangeable as we thought, opening the door to new forces, dimensions, and realms of understanding. The impact of this discovery extends beyond theory. The 3I/ATLAS anomaly may hold the key to unlocking revolutionary technologies once considered the stuff of science fiction. If this force can be harnessed, we could see breakthroughs in space travel, energy generation, and even the manipulation of gravity itself. Imagine a future where interstellar travel becomes possible, powered by a deep understanding of the forces that control space-time. Picture harnessing this force to develop technologies that allow for the direct manipulation of gravitational waves, potentially creating new methods of energy production that do not rely on conventional forms of matter or energy. But the societal implications are equally profound. With new discoveries come new ethical dilemmas and responsibilities. The power to manipulate the fabric of the universe itself carries immense risk, and humanity must be cautious in how it uses this newfound knowledge. The potential for harm is as great as the potential for good. As we stand at the cusp of this new scientific era, we must confront the responsibility that comes with it. What safeguards should be put in place to ensure these discoveries are used wisely? Who should control this knowledge? How can we prevent its misuse, particularly in military or exploitative contexts? The question of how humanity will approach the power of this anomaly is just as important as the discovery itself. In the past, scientific revolutions have led to both tremendous progress and devastating consequences depending on how they were handled. The development of nuclear energy, for example, has provided humanity with a vast source of power, but also led to the creation of weapons of mass destruction. Similarly, genetic engineering has opened opportunities for medical breakthroughs, but has raised ethical concerns about human enhancement and genetic manipulation. The potential for a similar duality exists here, with the power to manipulate space-time, a power that could either propel humanity into an era of unprecedented progress or lead us down a dangerous path. For now, the future remains open. The full implications of the 3I/ATLAS anomaly are still unfolding, and as research continues, the world watches with a mix of awe and caution. What will the future look like in a world where the laws of gravity can be altered, where new forces shape the universe, and where space-time itself may be manipulated? The possibilities are as exciting as they are daunting. The 3I/ATLAS anomaly has not only changed the trajectory of scientific discovery, it has altered the trajectory of human history. In the years to come, this discovery will undoubtedly be looked back upon as a turning point, a moment when everything changed. As we move forward, we must do so with a sense of wonder and humility, recognizing that the universe is far more mysterious and profound than we ever imagined. The road ahead will be one of discovery, shaping the future of humanity in ways we cannot yet fully comprehend. With each discovery comes the realization that the universe is deeper, more intricate, and more mysterious than we ever imagined. The 3I/ATLAS anomaly is no exception. While it has provided us with tantalizing clues about a new force that defies gravity and space-time, it has also opened up a vast expanse of unknowns, questions that remain unanswered, phenomena that remain hidden, and realms of existence that we have yet to explore. The deeper we look, the more we realize how much there is still to uncover. What lies beyond the known forces and dimensions? Could there be other forces interacting with space-time in ways we haven't yet detected? Could the universe itself be more dynamic and interactive than we've ever thought? These are the questions that the 3I/ATLAS anomaly brings to the forefront, signaling that there is much more to the cosmos than we currently understand. It forces us to reconsider the foundations of physics and our place in the universe. The discovery of the 3I/ATLAS anomaly is just the beginning of what may be the most exciting and challenging journey in human history. It forces us to confront the mystery of the unknown beyond, a frontier that will require new methods, new theories, and a deep sense of wonder and humility to navigate. In many ways, the 3I/ATLAS anomaly has made clear that we are no longer bound by the limitations of our previous understanding. For centuries, our theories of gravity, space-time, and the forces that govern the universe have stood as pillars of modern science. However, this anomaly challenges those very pillars, suggesting that there may be aspects of the universe that operate beyond our established models. It has revealed that the universe is far more complex and mysterious than we ever realized, and that the pursuit of knowledge is far from over. If anything, this discovery signals the beginning of a new era of exploration, one where we are not merely spectators of the cosmos, but active participants in uncovering its deeper secrets. The 3I/ATLAS anomaly opens a doorway to a new era of scientific discovery, one that demands we expand our perspectives and think beyond the conventional boundaries of physics. Could there be hidden dimensions of reality that we are yet to perceive? What forces might exist, undetectable to our current instruments, that are shaping the very fabric of space-time? The answers to these questions could alter the course of science and technology forever. It is a humbling reminder that, despite the strides we've made, there is so much more to understand about the nature of existence itself. The road ahead is uncertain, but it is full of promise. Whether we are uncovering new forces, discovering hidden dimensions, or redefining our understanding of space-time itself, one thing is certain: we're on the brink of something profound. The 3I/ATLAS anomaly may be the key to unlocking a future where humanity is no longer limited by the laws of physics as we know them, but instead guided by the infinite possibilities that lie ahead. This could lead to groundbreaking technologies such as new propulsion systems for space travel, advanced energy production methods, or even to manipulate the very fabric of space-time itself. The potential is limitless, but the challenges are equally immense. As we venture into this new frontier, the universe is not just a place to observe, it is a place to explore, to challenge, and to understand in ways that were once beyond our imagination. The unknown beyond is not just a mystery, it is an invitation to continue the journey of discovery, to challenge the boundaries of knowledge, and to seek answers to the greatest questions of existence. The 3I/ATLAS anomaly has shown us just how vast and infinite the universe truly is, and how much more there is to explore. This discovery has sparked a new era of scientific inquiry, one that will require not only new tools and theories, but a shift in our approach to understanding the cosmos. The journey is just beginning. With every new discovery, we move closer to understanding the deeper mysteries of the universe. Yet, in doing so, we also encounter more questions, more unknowns. The quest for knowledge is an ongoing process, one that will never truly end. The 3I/ATLAS anomaly is just the latest chapter in this ongoing story. As we uncover more about this phenomenon, we may find that it leads to answers we never expected, revealing truths that challenge everything we thought we knew. But in doing so, it will also inspire further exploration, pushing us to venture further into the unknown and to seek out new horizons of understanding. The universe has always been a source of wonder and curiosity, and with the 3I/ATLAS anomaly, we are now standing at the threshold of a new era of exploration. The journey ahead promises to be one of discovery, innovation, and transformation. But perhaps more than anything, it will be a journey of profound humility, a reminder that no matter how much we learn, the universe will always have more to teach us. The adventure is far from over. It is just beginning.